Hey guys. All right, so let's dig in. I'm going to give you a chance here today to make some discoveries about the volume of a sphere. So you can see a sphere is like a round ball. I mean, that's a 3D drawing. It's like a ball. It's got all those round sides. There's no flat sides. There's no faces, no corners, no vertices, which would be like corners. It's just nice and smooth and round, like a globe or a ball. So let's take a look at some of this. All right, so let's recall first the volume of a cylinder. And remember how you find that volume of a cylinder. The volume is equal to the pi times the radius squared times the height. And you remember that because we find that surface area down here of the base, which is a circle. So we're working surface area of a circle, which we know we can find by taking the pi times the radius squared. And remember, the radius is that from the center of the circle all the way out to the side. That doesn't look like it's in the center, but we're going to pretend like it is. So, and remember, 2 radii equals a diameter, because a diameter is the distance from one side of the circle through the center and across to the other side. So here we have a cylinder, and again, then we find that surface area of the base, the circle first, pi radius squared. But then we have to know, how deep is it? How much can I fill? How much space do I have here to fill? And we find that by multiplying it then times its height. Now, do you remember which solid it is that has its volume a third the size of the cylinder? Wow, get that one out. A third the size of the cylinder. You can kind of see that that would be breaking it down kind of into a third. Hopefully you remember that that's a cone. So recall the volume of the cone is that same volume formula we had for the cylinder. Here, maybe like that would be the cylinder. Only we're going to divide it by 3 because there's 3 of those cylinders. Because there's 3 of the cones that fit inside of the cylinder that has the same height and the same distance across there. Your diameter would be the same. So looking at this diagram, implication is pretty clear because you can see here that we have a cone plus a cone equal to the sphere. So that's implying to you that the sphere's volume is the same as 2 cones added together that have the same height as the sphere, and the cones have the same height. They also are going to have the same diameter. That first one I drew went a little crooked. It shouldn't be, but you know that. So again, we're going to look at how these 2 cones have the same height as this sphere has. Equivalent height. The radius for each also is the same. Okay, so here's a reminder. I have shown you that here is the formula to find the volume of this cone. Same thing here because the cones are the same height and same radius. And they're going to be equal to the volume of the sphere. So take a minute and think about what it would look like to add those 2 formulas together. So here's kind of an interesting fact as well. Think about what you know about a circle. You know that a circle from the center out to the side, that radius is going to be the same all the way around, isn't it? So likewise for the sphere, from the center of the sphere, which is in the center of the ball, where you can't really touch it with your hand, but you need to imagine it down there in the center, from that spot out to the outer edge of the ball would be its radius. And that radius from wherever in the center out to wherever to the edge, we're saying is the same as each of these cones pictured here. Well, that means that 2 radii, or the radii, 2 radiuses, end to end, are the same as the height of the sphere. So when you take this right there, it's the same as the height of that sphere. So that's kind of pretty cool, really, when you think about it, because that means if the height of these two cones, each of these cones, is the same as the height of this sphere, I would guess the diameter would have to also be equivalent to the height of the cone, because the diameter of the sphere would have to also be the same, and that diameter, which is the 2 radius, is the same as the height. So I think we can assume that if you have a cone with the same height and radius as a sphere, that that cone has the same height as it does a diameter. So let's look at this. Knowing that the height is the same as 2 radius, keep in mind that that means h here, h there is going to be equal, here's h, it's equal in measure to r plus r, or h is equal to 2r. Go ahead and take that h out, put r plus r in place of each of the h's. Remember, here is where the height went in the formula for the cone's volume. Additionally, I see here that my squared for my original radius squared, somehow that squared fell off. So that's still pi r squared, because remember we just took that formula that was pi r squared times the height, and we took out the height and put in r plus r because its equivalent is the height. All right, so I've replaced r plus r with 2r, because just like if I had 2 plus 2, well, let's use a little bit of a different example. 2 is never good for this, because 2 2's is 2 2's. It's not very definitive. If I had 3 plus 3, that's the same thing as saying 2 times 3. Well, if I said r was equal to 3, I could say r plus r is equal to 2 times r. Let's do a quick recap of what we've done here, of what's happened with our volume formula for the cone. Just recall, the volume for a cone is found by taking pi times radius squared times the height, all divided by 3. Okay. I want to remind you that pi times radius times height divided by 3 is the same exact value. I just expanded out the multiplication. All right. Well, then what we did was we remembered or recalled here that the 2 radiuses end to end are the same measure as the height. So we're going to take this, that h, and we're going to replace it with r plus r, which is 2 times r. Remember the example I gave with 3 plus 3 is equal to 2 times 3. So r plus r is equal to 2 times r. And I'm going to rewrite pi r squared times 2r divided by 3. Now let's expand that out like we did in the blue when we did it in blue. I'm going to move over here to green. Red's kind of harsh. And that means we have pi times r times 2 times r divided by 3. Same thing, just expand it out. And recall, commutative property of multiplication means I can multiply those factors in any order. And we're going to choose to go ahead and do it in the order where the coefficient, the 2, is in the front. So we're going to have 2 times pi times, and then how many factors of r do I have here being multiplied? I have 3 of them. Remember our exponents. I've got 3 factors of r. That simplifies to 2 pi r cubed divided by 3, and that's the same thing here for that volume of one of those cones. Crazy, isn't it? I just substituted my height for my 2 radius, and it only works because the 2 times the radius is the same as the height. Remember, we talked about the diameter and the height being equivalent in this example. So here you can see that coming together where you have one cone here, 2 times pi r cubed divided by 3, plus a second cone, 2 times pi times r cubed divided by 3. And guess what? That equals the volume of a sphere. So what happens when I add those together? So let's look at the mathematics involved here. I know this is kind of a hard part for some of you, but I know you can do this. You're getting so much better at it. I want to look at evaluating what we have as an equation. 2/3, because if I have 2 times pi times r cubed divided by 3, I can take that out and say it's the same as 2 times pi times r cubed times, remember, 1/3. Multiplying by 1/3 is the same as dividing by 3. And if I take the coefficient here and multiply it times the other constant of 1/3 there, they're going to together equal 2/3. Okay, so that's where I got my 2/3. So 2/3 times pi times r cubed plus 2/3 times pi times r cubed. What can I do here? I have this quantity and that one. And think of these, the 2/3 right here, 2/3 factor, factor. Oh, that didn't turn out very nice. Let me undo that. Let's try that again. Factor times a factor times a factor. That equals 2/3 pi r cubed. I'm going to add to that the same number with the same 3 factors. So let's think about the common factors that we might be able to take out, like reverse distributive property. So that 2/3 can come out to the front, can it? And we can have 2/3 times pi r cubed plus pi r cubed. That doesn't really help me much. What if I decided instead of doing this one, that I go ahead and I say, well, you know what, I think I'm going to take out pi r cubed. Each of these factors from both of these would mean I'd have to multiply that times 2/3 plus 2/3. Keep in mind, if I distribute this monomial to each of those 2/3, I'm going to have that 2/3 pi r cubed plus 2/3 pi r cubed, back where I was before. But I'm trying to find some way that I can simplify this equation, 2/3 pi r cubed plus itself. So let's look at what that could look like. Aha, there it is. 2/3 plus 2/3 times pi r cubed. That is the volume of a sphere. Oh, but wait a minute. 2/3 plus 2/3, I can simplify that further, can't I? Absolutely. Because I know that if I have 2/3 plus 2 more thirds, it's the same as saying 2 plus 2 as thirds, which is good. So if I add those together, I'm going to have 4/3, and there we have it. Until I have a value for the radius, I can't do anything more with that formula. So that is the volume of a sphere. 4/3 times pi, radius cubed. Or you might see it written 4 times pi r cubed divided by 3. Because remember, that divided by 3 there is the same as multiplying times 1/3. Same thing as dividing by 3. And if I have 4 times 1/3, it's equal to 4/3. Hopefully you found some things here that were kind of interesting to you. I know it's pretty lengthy and seems pretty complicated, but I think you're going to find it pretty cool. And I think it's nice to see how all these things come together and actually have true meaning. and fit together like things do in the real world. Could be very important skills when you, in any job, not just putting leftovers into containers, but having an idea of how things are going to fit together. If you get into a job where you have to look at packing items for shipping or fitting things onto a shelf, it's very good to get a visual and an idea of how different shaped items can fit into different shaped spaces.